Hi everyone.
Hi everyone.
So this is lesson 10.1 over 3 part 1. While it's 3 sections in your textbook, we're going to split the 3 sections into 2 days. And this is the first. So we're going to start tackling parametric and vector functions. We're going to do a little review of them that you should remember from pre-calculus, but probably need a refresher, and then we'll dig into the calculus. So in algebra, equations are generally graphed in 2 variables, x and y. Now what we're looking at is equations that are going to be expressed as functions x and y, which are functions of t or theta. And that t or theta is called the parameter. That third variable is called the parameter. And there's a separate equations for x and y that are called parametric equations. X is going to describe that horizontal movement, and y is going to describe the vertical movement based on that parameter. So without a calculator, we're going to make a table and sketch the curve that is given here in example 1. X equals t squared minus 4, and y is equal to t over 2, or 1/2 t. And t is only going to sit from -2 to 3. So you can see I've already made a table here, and I'm just going to start filling that in and evaluating x and t at those values. So when I plug in -2 to x, let's just do x first. So I'll plug in -2 to x, and I get a 0. When I plug in -1, I get a -3. When I plug in 0, I get a -4. When I plug in 1, I get a -3. When I plug in 2, I get a 0. And when I plug in 3, I get a 5. Next, I'll go ahead and plug in those same values to y. So when I plug in -2, I return a -1. When I plug in -1, I return -1/2. When I plug in 0, I get a 0. When I plug in 1, I get a +1/2. When I plug in 2, I get a 1. When I plug in 3, I get a 3/2, or 1.5. And so now what I'm going to do, let me move this over a little bit, is I need to graph this on a coordinate plane. So it looks like for x, I'm going to need to go out to +5 and to -4. And for y, I need to go from -1 up to +1.5. So I'll go up to 2. And now let's go ahead and graph these. So I have 0, -1, -3, -1/2, -4, 0, -3, +1/2, 0, 1, and then 5, 3/2. So you can see I start at 0, -1, and then I can see the movement of my curve. And usually for a parametric curve, I also need to provide this arrow that indicates direction. So next you can verify on your calculator. I don't have the capability to show my calculator screen, but what you want to do to verify on your calculator is change the mode to parametric mode. You do that by going to the mode, and then it's probably going to be in a rectangular or coordinate mode or function mode. It depends on what calculator you have. And you'll click over on the options to parametric mode. And that's going to change your y equals. So when you go to put in a function, it'll now say x sub 1, y sub 1, and then your t or your theta is going to be available to you there too. So you can do that on your calculator and verify. Then what I'd like you to do in this next exercise is to plug in a couple more functions. I'd like you to plug in this function and change your parameter to go only from -1 to 1.5. And then I'd like you to plug in this next one here and only go from, this is -pi/2 right here. And then it looks like pi/4, I would guess. But you can plug in these decimals if you'd like to. And you'll notice that all 3 of these parametric curves, the one we did by hand, and these following 2, they're all going to produce the same, what's the word I'm looking for? The same curve. Next, what they ask us to do is to eliminate the parameter. So if I'm going to eliminate the parameter, what I usually do is I want an equation y equals and then some function of x for a rectangular function here. So what I'll do is I'm going to solve for t in this x function. So I'll have x plus 4 equals t squared, and then I'll take the square root of both sides, finding that t is equal to plus or minus the square root of x plus 4. And then what I'm going to do is I'm going to sub this t in for y. So then I'll have y is equal to t over 2, which means that is equal to plus or minus the square root of x plus 4 all over 2. Or I can just say y equals plus or minus 1/2 times the square root of x plus 4. And you can see while this is not going to be a function because it's going to have 2 outputs for every input. If I were to graph this equation right here just as it looks, I can see it's a square root function that has been shifted to the left 4, and then it has had a vertical shrink by a factor of 1/2. So if the domain is all real numbers, this would be the top half. So this right here would be the plus part, and then the minus would be right here. So you can see that's going to be my rectangular graph. However, I do have some domain restrictions here. So I'll have to add within this that for my x values, I have -4 is less than or equal to x is less than or equal to 5. And for y, -1 is less than or equal to y is less than or equal to 3/2. So I have these additional restrictions on x and on y if I'm looking at the rectangular coordinates. So while rectangular equations on restricted intervals show the path, parametric equations will also show the path, but they will also tell us about the speed and the direction of a particle that's moving along these curves. So this would be the new part, the speed and the direction. So for example 2, we want to do the exact same thing we did in example 1 with these 2 other equations. X of t equals 2 plus 3 cosine of t, and y of t equals -1 plus 2 sine of t. All right, so let's plug in values for x of t first. Notice that I have various angle measures in radians because of that cosine and sine that are in my functions. So when I plug in 0 for x, I get 5. When I plug in pi over 2, I have 2. When I plug in pi, I have -1. 3 pi over 2 gives me a 2, and 2 pi gives me a 5. Notice that I chose the 4 corners on the unit circle because those would be easy to plug in. I may have to reevaluate if it didn't give me enough information and dig deeper. Maybe plug in pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, and maybe even go into plugging in pi over 6 and pi over 3 if I need to. But this one should be good. So next I'm going to plug in these values to y. I'm going to get -1, +1, -1, -3, and -1. And now we can graph this. So it looks like I need to go from -1 to 5 on my x-axis, and I need to go from -3 to +1 on my y. All right, so let's plug in these points. So I have 5, -1, +2, +1, -1, -1, to -3, and then back to 5, -1. So if I'm following these points, we're going in that direction, and I can make an arrow there to indicate direction. You can also put another arrow if you wanted to continue that direction. And this is looking very much like an ellipse to me with a center. I think at 2, -1 is where it looks like that center is. You can see the change here is 2 and here is 2. And then you can see the change here is 3 and here is 3. So I'm pretty sure this is an ellipse. And I can confirm algebraically by changing this into a rectangular equation. This is going to be a little different though, because my approach on the last problem, if I look up here, was to go to my x equation and solve for t, and then plug that in the y equation. Here, this would be really messy, because if I solved for t in my x equation, I'd have a cosine inverse. Then I'd be plugging that equation with a cosine inverse into a sine, it'd be pretty messy. So instead, let's take a different approach, and let's isolate cosine of t and sine of t in each equation. So in my x equation, I'll have x minus 2 all over 3 equals cosine of t. And then in my y equation, I'll have y plus 1 all over 2 equals sine of t. And now, how can I combine these two? Well, think about what you know about sine and cosine. My Pythagorean identity says sine squared t plus cosine squared t is equal to 1. So what I can do is I can square sine and cosine, and I can do that as long as I square both sides of my equations. And that will give me sine squared of t is y plus 1 squared all over a 4. And cosine squared of t, so 2, is going to be equal to x minus 2 squared all over a 9, which equals 1. And then typically with an ellipse, I'll have my x in front of my y. But you can see this is standard, oh, that should be a 4. This is standard notation for an ellipse. I can see the center of my ellipse is 2, negative 1, just like I thought it was going to be. And I can also see here this 9 and this 4. The square root of those represents the distance that I'm going out from my center in a vertical and horizontal direction. So here I have this equation that was a parametric curve written in rectangular coordinates, and you can see how we did that. All right, so now that we've spent some time reviewing parametric equations and functions, now we are going to dig into the calculus. So let's take a look at our first parametric equations and formulas for calculus. Sorry, I'm making this a little bigger. Okay. So the first we have, if a smooth curve C is given by equations x equals f of t and y equals g of t, then the slope of C at the point xy is given by dy dx equals dy dt over dx dt, where dx dt is not 0. So this right here is my first derivative. I believe that you should have learned that back when you first learned about derivatives. Dy dx, the rate and change of y with respect to x, is just dy dt over dx dt. Now the second derivative is a little more complicated. Remember our notation here for our second derivative. And it is going to be equal to the derivative with respect to x of dy dx. The issue is when you have dy dx, it is most likely going to be written in terms of t due to the parametric nature of these equations. So what that means is when you're taking the derivative with respect to x of dy dx, first you're going to want to take the derivative with respect to t of dy dx and then multiply that by dt dx. And therefore what that means is we're really just going to this system where we're going to take the derivative with respect to t of dy dx, and then in order to get that differential to match up, we're going to divide by dx dt. So here, if you want to write this in words, if this is helpful right here, you're going to take the derivative of dy dx with respect to t. So WRT is with respect to t. Then you are going to divide by dx dt, and then simplify if needed. Now let's take a look at examples so that we can get some practice. So without a calculator, given that x is equal to 2 times the square root of t and y is equal to 3t squared minus 2t, we're going to find dy dx and the second derivative of y with respect to x, and we're going to evaluate at t equals 1. So first, dy dx is equal to dy dt over dx dt. Dy dt is going to be 6t minus a 2, just a simple power rule. And the same thing here, if it helps you to write x as 2 times t to the 1/2. Dx dt is just going to be t to the negative 1/2. You can clean this up. You can write this as the square root of t times 6t minus 2 if you'd like. or you could leave it, it's up to you. And next we're going to evaluate this at t equals 1. So when I plug in a 1, I just end up with the square root of 1 times 6 minus 2, which will give me a 4. Next, what we're going to do is find that second derivative. So the second derivative of y with respect to x is going to be equal to the derivative of dy dx that I just found with respect to t over dx dt. So I could even go ahead and just put that here, because I know that's going to be there. And now we need to take the derivative of y with respect to t that we just found. So what I think I'll do is I think I'm going to go over to the side and rewrite, let me get a different color. I'm going to rewrite this as t to the 1/2 times 6t minus 2. And now I'm going to distribute this. So I'll have 6t to the 3/2 minus 2t to the 1/2, just because it's going to be easier now to take the derivative and use a power rule. So if I use a power rule here, I'm going to multiply the 6 times the 3/2, and that just gives me a 9. And then I'll have t raised to the 1/2. Minus 2 times a half is just 1, so t to the negative 1/2 here. So now when I clean this up, this becomes t to the 1/2 times 9t to the 1/2 minus a t to the negative 1/2. And then when I distribute this t to the 1/2, I have 9t minus a 1. And now I'm going to box that up. When I evaluate this at t equals 1, I'm just left with an 8. So there is your first practice with finding the first and the second derivatives of a parametric curve. So in the next example, without a calculator, given that x is equal to 4 cosine of t and y equals 3 sine of t, I want to write an equation of the tangent line to the curve at the point where t is equal to 3 pi over 4. So let's remember, what do we need for the equation of a tangent line? I always need two things. I need a point and I need a slope. That's the only two things you need for a tangent line. Let's find the point first, because that's going to be easier. If I'm looking at t equals 3 pi over 4, x will be equal to 4 times cosine of 3 pi over 4, and y will be equal to 3 times sine of 3 pi over 4. So cosine of 3 pi over 4 is going to be negative root 2 over 2. So cleaning this up, x is just going to be negative 2 root 2. And sine of 3 pi over 4 is positive root 2 over 2. So when I clean this up, I have y equals 3/2 root 2. So my point is done. I have negative 2 root 2, 3/2 root 2. And now for my slope. To find the slope, I'm going to need to find the first derivative. So my derivative dy dx is equal to dy dt over dx dt. So that's going to be equal to, let's see, 3 cosine of t, and then dx dt is going to be negative 4 sine of t. When I evaluate this at t equals 3 pi over 4, I have 3 times negative root 2 over 2, all over negative 4 times positive root 2 over 2. So this is nice that these root 2 over 2s are just going to cancel. The negatives are going to cancel, becoming positive, and I'll just get 3/4 for my slope. So now the only thing left for me to do is put it all together for my tangent line, and I'm going to use point slope form. I'll have y minus 3/2 root 2 equals my slope, 3/4, times x minus a negative 2 root 2. And so there's the equation of my tangent line for this parametric curve. All right, in the next example, without a calculator, I want to find all points of horizontal and vertical tangency given the parametric curve x equals t squared plus 2 and y equals t squared minus 3t plus 5. So let's think about horizontal and vertical tangency and what that means. if I'm looking for horizontal and vertical tangents, I'm really looking for where my derivative is equal to 0 or where my derivative is undefined. So horizontal would be where the derivative equals 0. We can write that. I actually would prefer not a highlighter. Where the derivative equals 0, and here is where the derivative is undefined. So let's find the derivative. Let's start there. So dy dx equals dy dt over dx dt. So dy dt is going to be 2t minus 3. Dx dt is going to be 2t plus a 1. So now what I need for a horizontal tangent, that's going to exist when my numerator here equals 0, so long as my denominator doesn't at that point. So that would going to be when t is equal to 3/2. And then I just need to check and make sure 3/2 doesn't make my denominator 0, which it doesn't. My vertical tangent is going to be when the denominator is equal to 0. And that would be t equals -1/2. So it says, without a calculator, find all of the points. So I don't know if we've really answered the question yet, because I have found the t values where these exist, but I haven't really found the points. So in order to find the points, I need to take my t values and plug them into my x and y equations so that I can actually find the points. When I plug in t equals 3/2 to x, I get 15 over 4. And then when I plug it into y, I get an 11 over 4. So this is going to be the point of horizontal tangency. And next I'm going to plug in t equals -1/2, which is going to give me -1/4 for my x value, and then 27 over 4 for my y value. And so that is going to be my point of vertical tangency. So we're cruising right along. If you're looking for a nice breaking point, now is probably a good time to pause the video if you're wanting to take a little break before we go through the rest of the notes. We still have to talk about parametric arc length, and we're going to do an example there. We're going to look at just a nice summary before we wrap up with 2 more examples. So the next thing that we're doing is parametric arc length. So we had done arc length of a function back in section 7.4. And what we had found there was that arc length was equal to the integral from a to b of the square root of f prime of x quantity squared plus 1 dx. So that was for a rectangular function. With parametric arc length, it's just a little different. We're still going to have the integral from a to b, where a and b are going to be t values. And it's going to be equal to the derivative of x with respect to t squared and plus the derivative of y with respect to t squared. And so here we have an example. Without a calculator, we're going to find the arc length of the given curve from 0 to 1. So let's just dig right in by starting to take these derivatives. dx dt is going to be 2t, and dy dt is going to be equal to 12t squared minus a 0. And next I'm going to have to square these. So in my next step, when I square these, I'm going to get 4t, and then I'm going to get 24t to the 4th. So next I'm going to put these in my arc length formula. All of arc length is equal to the integral from 0 to 1 of the square root of 4t, which was dx dt squared, plus 24. Glad I caught that mistake. Not 24, I'm crazy. 12 squared is 144. So plus 144t to the 4th dt. And now it is time to simplify. Look, I found another mistake. If you guys were all in class with me, you would have caught these already. We would have cleaned that up. So we have, dx dt is just 2t. dx dt squared is 4t squared. So let's make sure we add that in. All right, now I'm ready to move forward. Maybe I'm the one who needs to take a break. All right, let's roll on. So I'm feeling like I can factor out a 4t squared, which would leave me with 1 plus 144 over 4 is 36t squared. And then I'm going to be able to pull a 2t, maybe should have given myself a little more room there, got it overly ambitious, a 2t out of that radical. And now I'm feeling a u sub. I'm sure you guys were feeling it too as we were writing that out. So if u is equal to 1 plus 36t squared, du is going to be equal to 72t dt. So if I'm rewriting this integral, I like to re-index. So if I'm going to plug in my 0, my u becomes 1. And if I plug in 1, my upper limit of integration becomes a 37. Let's see, if I multiply, I have a 2t, so if I want this 72 to be a 2, I'm going to multiply by 1 over 36. So this would become 1 over 36 du equals 2t dt. So I'm going to be replacing all of this with a 1 over 36. Then I have u to the 1/2 just times du. So just so everyone can make sure we've put all this together, this 2t dt here is being replaced with 1 over 36 du. The square root of 1 plus 36u squared is being replaced with this u raised to the 1/2. And then I went ahead and I re-indexed, plugged in 0 to u, and I got a 1. Plugged in the 1 to u, and I got a 37. All right, so now that everything is color coordinated, hopefully you see where everything is coming from, and I can evaluate. So when I take the antiderivative of 1 over 36 u to the 1/2, I end up with 1 over 36, which is just hanging out, 2/3 times u to the 3/2. I'm going to evaluate from 1 to 37. I can clean this up a little bit, pull a 2 and get this to be an 18. So then I'm just left with 1 over 18 times 3 is 54, u to the 3/2, evaluated from 1 to 37. So now I have 1 over 54 times 37 raised to the 3/2 minus 1 over 54 times 1 to the 3/2. Luckily that's just going to be a 1. So I'm left with 1 over 54, 37 to the 3/2 minus 1 over 54. And I'm going to leave it like that. You could clean this up a little more, like if you really wanted to. If I have 37 raised to the 3/2, just reviewing this, this is going to be the same thing as 37 times the square root of 37. So you're welcome to simplify that up a little bit, but it's really not necessary. It's not really going to get much prettier. So that's going to be the length of the curve that is produced by this parametric equation. All right, so next what we have, hopefully you'll find this really helpful as we build on this material, is horizontal and vertical velocity component vector information. Sorry, I'm trying to get this to be like straight. So when dealing with parametric curves, often we're talking about particles that are moving with these speed and directions throughout this path. So it's important to understand what you're talking about when you're taking these derivatives. So x prime of t, or dx dt, is the rate at which the x-coordinate is changing with respect to t, or the velocity of the particle in its horizontal direction. Y prime of t is essentially the same thing, just talking about the particle's vertical direction. Parametric curves are very easy to represent as vectors. And I know we haven't talked about vectors at all in this course because I know you talked about them in your pre-calculus course last year, and we just haven't expanded on that knowledge. But we're getting into that now. So whenever you're given a parametric curve, it always has a vector representation, which is just going to be your vector of your horizontal position, which is x of t, comma, your y of t, your vertical position. And that is going to be your position vector, which is often s. Then your derivatives are your velocity vector, which is just going to be x prime of t, y prime of t. And then the second derivative is your acceleration vector, x double prime of t, y double prime of t. Please note that this is different than dy dx and the second derivative of y with respect to x that we started with, that we did back in examples 3 and 4. This is different. Note that vectors may or not be contained with the chevron notation. It is usually what I'm going to use, but it could be different. So again, just going with that note that it's different than the dy dx and the second derivative, that's what I've noted here in the next two bullets. dy dx is the rate of change of y with respect to x, or the slope of the tangent line to the curve, or the slope of the position vector. The second derivative with respect to x is the rate of change of the slope of the curve with respect to x. That is different than taking derivatives with respect to t, which is what you're doing when you're finding those velocity and acceleration vectors from the position vector. All right, so next is the definition of the speed of the particle, and this is really important. It's going to come up a lot. So if you have these are not absolute value signs. I know they feel like absolute value signs, but they're not. This is going to be notation. Sometimes there's double lines, but this is notation for the speed of a particle. When the speed of the particle is simply the magnitude. If you go back into your knowledge of parametric equations and vectors from pre-calculus and combine that probably with what you've learned in physics, you'll remember that speed or magnitude of a particle is basically the square root of dx dt squared plus dy dt squared. It's basically like an expansion of the Pythagorean theorem. And next we just did arc length. So this is our arc length formula that we have here. And we just did an example with that. And remember, the arc length of a formula is also going to be the total distance traveled by a particle. If you have some curve, looks like this, and you find the length of that curve, that is going to be the total distance traveled by that particle. We're in a little bit of a different world from rectangular coordinates. So if you remember that an integral is displacement, and the absolute value of the integral of the absolute value of a function, that's going to be distance traveled. This feels a little different because we're in a different world with these parametric and vector equations, which is why I've noted it right here. The absolute value from A to B of the absolute value of the velocity function is the total distance traveled, whether it's going to be a straight line or a curve. So all of this is just for summary, for reference, because I know it's a lot of information. And we're going to do a couple more examples to solidify all of it and hopefully put all of our pieces together. So in example 7, it says a particle moves in the xy plane so that at any time t greater than or equal to 0, the position of the particle is given by these parametric functions. X of t is equal to t cubed plus 4t squared, and y of t equals t to the 4th minus t cubed. What I'd like to do now is just note that these are parametric equations, and their corresponding vector equation, position vector, is equal to the vector t cubed plus 4t squared, comma, t to the 4th minus t cubed. So that is its corresponding position vector. Our question says, find the velocity vector at t equals 1. And let's just do the first part because there's an a, b, and c to this. So the velocity vector at t equals 1, first let's find just the velocity vector in general. It will be 3t squared plus 8t, comma 4t cubed minus 3t squared. And now if I evaluate this at t equals 1, so the velocity at t equals 1 is going to be equal to 11. And then when I plug in 1, I get a 1 here. So that's part A. Now let's look at part B. It says find the speed of the particle at t equals 1. So if I'm finding the speed of the particle, remember that's going to be the magnitude of this vector. So it is the magnitude of the velocity vector at t equals 1. So if I'm finding the magnitude of this velocity vector over here, it's going to be equal to the square root of 11 squared plus 1 squared. It's because I'm looking at this right here. So therefore, the magnitude is just going to be equal to the square root of 122. So I would say the absolute value, the magnitude of the velocity vector evaluated at 1 is equal to the square root of 122. And you can use the double lines here, or sometimes you just have the single lines, depending on what notation you're using. And then C says find the acceleration vector at t equals 1. So let's find just the acceleration vector in general. So I'd have 6t plus an 8, comma 12t squared minus a 6t. And now if I'm evaluating that, so the acceleration vector evaluated at t equals 1, that's just going to give me 14, comma 6 when I plug in a 1. So hopefully what this example does is it shows you, one, how you can represent a parametric curve as a vector. Then you can find the velocity vector and an acceleration vector. You can evaluate those at specific points, and you can find the speed of a particle by just finding the magnitude of the velocity vector. So this, again, this is just the speed of a particle. It is the magnitude of a velocity vector. All right, let's look at our last example. I believe it's the last one. Sure is. So a particle moves in the xy plane so that x equals root 3 minus 4 cosine t and y equals 1 plus 2 sine t, and we're only looking from 0 to 2 pi for t. So I'm going to find the first and the second derivatives with respect to x. So dy dx is going to be equal to dy dt, which is going to be negative 2 cosine t, over dx dt, which is just going to be a positive 4 sine of t. So we could write that as negative 1/2 cotangent of t if we wanted to clean that up. Now the second derivative, oh wow, notation. So the second derivative of y with respect to x is going to be equal to the derivative of dy dx with respect to t. So I'm taking the derivative of negative 1/2 cotangent of t, which is going to be positive 1/2 cosecant squared of t, all over dx dt, which was 4 sine of t. And if I clean that up, I'll get 1/8 cosecant cubed of t. So it's great that you have these examples 7 and 8 back to back, so you can see the difference between working in vectors and dealing with vector and vector velocity and vector acceleration versus my derivative with respect to x, dy dx, and the second derivative with respect to x. All right, last thing, it says the path of a particle intersects the x-axis twice. Write an expression that represents the distance traveled by the particle between the two x-intercepts. So let's figure out when this thing is going to intercept the x-axis. So that's going to happen when y is equal to 0. So if I find when y is equal to 0, I'm looking at 1 minus 2 sine of t equaling 0. And when I solve for sine of t, I end up with sine of t equals 1/2. And I know that happens twice along the interval from 0 to 2 pi. Happens at pi over 6, and then again at 5 pi over 6 in quadrants 1 and quadrants 2. So if I'm trying to find the distance traveled by the particle, I really want to know the length of the curve from pi over 6 to 5 pi over 6. And to find that, I need to do dx dt squared. So dx dt I found was 4 sine t. So I'll have 4 sine of t quantity squared plus dy dt squared, which was negative 2 cosine squared of t. And then dt. It says don't evaluate, it just asked me to write an expression, so I don't even need to clean this up. Oh wait, I have an error. Look at my notation. Gotta make sure this is accurate. So it's gonna be